All right, we're gonna go over the physical homework today. On Wednesday, we'll go over the Daylink homework and do the review. Daylink homework was easier anyway. And then we'll be all set for doing the midterm, starting Friday night, right?
Sweet.
Friday night. Okay.
And you have to get done before this Saturday or the Saturday after?
This 8 days, this Saturday after. Or Sunday after, whatever. 2 weekends is what we decided. Okay. All right. So the first question was FedEx bandwidth. You have 6 terabyte hard drive and a FedEx drone that can move the drive from LA to New York in exactly 24 hours. What's the effective bandwidth?
1 point.
What's the problem? So we have a 6 terabyte hard drive, right? And that is in 24 hours, right? That's our bandwidth. So 6 terabytes is how many bits?
1024 times 1024 times 1024 times 6.
Yeah, or even easier, 6 times 2 to the 40th, which is what you just said, times 8 to make it bits, right? Or bytes. Over 24 hours. And that comes out to really, it's like, if you do the math, it's really close to 600. It's like 592, I think. Megabits per second. Most of the problems here, almost everybody got that right, with the exception of terabytes. Hard drive is measured in 2 to the something, and terabits in network is measured 10 to the something. So it was just 1 point. So remember, storage is measured in powers of 2, and network is measured in powers of 10. That's it. Second one, a noiseless 8 kilohertz channel is sampled every 1 millisecond. What's the maximum data rate? Trick question. It tricks you into running Shannon, or running Nyquist. But Nyquist tells you how many samples can be extracted out of a waveform, right? Not how many levels. So if there is noiseless, there's no signal to noise ratio, it means that noise is 0, which is divided by 0, so the effective bandwidth is infinite. Because whenever you hit the ceiling, you can just make more levels, right? And you can encode more bits into every waveform. So it doesn't really matter how many waveforms there are if you can encode an arbitrary number of bits in there. So the next one is basically the same thing, except for we have a 30 decibels of noise. Our signal noise ratio is 30 decibels. So, what does that look like? So now we have an 8 kilohertz channel. And we have 30 decibels of noise ratio. So what is the formula to solve this thing? Yes, it's Shannon, right? B, the second log of this. Except for this is expressed in decibels, right? Which is not the actual ratio. So we got to figure out that. So what does that equal?
10 to the third?
Huh?
10 to the third?
10 to the third, right? And that is 1,000 plus 1. And so you get 1001, which is really close to 10. right? So it's approximately just short of 10. So it's just short of 80,000 bits. Or 80 kilohertz, just short of it. I think it's 79, whatever, but if you put 80, I just gave it to you, because it's just short of 10. 79.7, I guess, is the real answer. The next one, a T1 carrier, and I give you what that is, which is 1.544 times 10 to the 6 over a 50 kilohertz line. What's the maximum signal noise ratio? So it's the same formula as last time, Shannon, right? Except for now we have to solve for the signal noise ratio. So Shannon's B log 2 the signal to noise ratio plus 1. And so now you have 1.544 times 10 to the 6, right? A T6 line, or a T1 line. I just gave that to you. And that equals what? 50,000. Because I gave that in the problem also, right? 50 kilohertz. Log 2 of 1 plus S over N. And we're solving for S over N, right? So we can divide this out. So this is now 1.544 times 10 to the 6 divided by 5 times 10 to the 4th equals log 2 of 1 plus Sn, which comes out to 30.88 equals log 2 of 1 plus Sn, right, which means that is 2 to the 30th dot 88 equals 1 plus Sn. This is a really, really big number. It's 197608793 because we can subtract the 1 over there, equals Sn. This is why we measure things in a logarithm scale, right? So we didn't explain that over there, right? So that's signal to noise ratio. We want it in decibels. So 10 log base 10 of that really big number equals 90, approximately 93. It's 93.958. So 93 decibels. We get that one? Almost everybody get that one right. All right, we have a 12 megahertz wide channel. How many bits can be set with 8 signal levels? This is the exact same thing. Do we need to go over it? This one's really easy. You just plug everything into Shannon. All right. Then we came to the ones that this is where things start to go bad. How much bandwidth is there in 0.1 microns of the spectrum at a wavelength of 100 microns?
So you said number 5 was Shannon, not Nyquist?
Yeah,
The 12 megahertz wide.
It's Nyquist.
Yes, it's Nyquist, sorry. Yes, sorry.
Do you have the answer for number 5?
Yeah, let's do that. So, the answer is, counting zeros here, 72 kilobits, or megabits per second. But let's do it. All right. So Nyquist is 2b log 2b, right? So, and we have 12 megahertz and 8 levels. Right? So that is 2 from there. B is 12 megahertz, so 12 million. Times, let's just go ahead and do this. 12 times 10 to the 6 or million. Times log 2 of 8. Log 2 of 8 is 3. So then we get 2 times 12 times 10 to the 6th times 3, which is 72 times 10 to the 6th. All right, now let's go into the hard ones. How much bandwidth is there in 0.1 microns with a spectrum at a wavelength of 100 microns? So we're looking for bandwidth, right? What kind of bandwidth?
The delta.
The delta of the electrical engineering type bandwidth. We're looking for a frequency, right? So a delta frequency is what we're looking for. What is that? All right, so the information we have is the wavelength is 100 microns, so 100 times 10 to the negative 6 meters. And we're going to do 0.1 microns. So our delta is 0.1 microns. There are 2 ways to do this. I'm going to do the hard way first because it's very intuitive. And then there's a way to derive, if you span both ways, you can come up with an easier formula. So, first way, we're looking for a delta frequency, right? So we need frequency minus frequency prime is what we're trying to find out. Okay, well, frequency is equal to the wavelength times the speed of light, right? Is that correct? Speed of light is equal to frequency times wavelength, right? So frequency so we can divide by wavelength to get frequency, right? So here we go. There we go. So F1 minus F prime is what is our delta F, right? So F1 or F is so that's the speed of light over 100 times 10 to the negative 6th, right? Minus the speed of light over 100.1 times 10 to the negative 6th. And we could just solve for that. They're going to be crazy big numbers, right? Because speed of light is is 3 times 10 to the 8th, right? So, and we could simplify that to the 4th, right? So we're still gonna have 3 times 10 to the 12th over 1, minus 3 times 10 to the 12th over 1.001. Does that make sense? If you round very much, it's going to get, your number's going to be rather off, right? So, we did it if, in that solution, we made one frequency higher than the other. Right, so if we have our spectrum, right, where it's getting closer and closer and closer, right, I talked about this before, if you pick a way, if you go this way, you have more bandwidth than if you go that way, the same distance. So you can get slightly different answers because you could also have done this. Because we're really just looking for the, or actually, sorry. You could really have subtracted these two, or you could have subtracted the other way and done the absolute value of it. Because frequency is simply the distance between the two. Doesn't matter which one goes first. And you would come up with a slightly different answer. The other way to do it is to split the difference. If you split the difference, you can actually derive this. You can derive the delta frequency equals C times the delta wavelength divided by the wavelength squared, if you split the difference. And it's because there's something magical that happens when you take a number minus another number and multiply by the number plus the number. Right? So you get a quadratic that's easily solvable, voila, and you can derive this. So if you do this, then you can simply just plug in the numbers. Notice that if you do this, you'll come up with the average bandwidth of whether you subtracted one way or the other. If you took the average, because you're splitting the difference. All ways are right, because I didn't ask one way or the other. If I did ask one way, say that you were allotted a frequency from or allotted a wavelength from 100 microns to 110 microns, and you're going to use the first 0.1 micron. It can only be solved this way because you can no longer split backwards. All right. The next one. This was right out of the book, so everybody got this right.
What was the answer to that one?
Oh, sorry, it's 3 gigahertz. And really, it comes down to moving the decimal point over 3 when you were at 3 to the 12th to begin with. All right, so the next one. Radio antennas work best when the diameter of the antenna is equal to the wavelength of the radio wave. Antennas can be engineered with a diameter of 1 centimeter to 5 meters. What frequency range does this cover? Well, this is the same speed of light ratio. So C equals the wavelength times frequency, right? And it says we're going to give you the wavelength. Antennas are engineered to the same wavelength, right? So we got to solve for 1 where lambda is equal to 1 centimeter, and 1 where lambda is equal to 5 meters. So in the first case, it would be frequency is equal to 3 times 10 to the 8th, which is speed of light, over 0.01, 1 centimeter. Well, that turns out to be easily solved with 3 times 10 to the 10th, which is 30 gigahertz. The next one is frequency is equal to speed of light again, over 5, which ends up being 60 megahertz.
So for that question again, just begs the question. So should a Wi-Fi antenna be 10 centimeters?
It does beg that question. So they work best. So back when Wi-Fi was very young, I bought off of eBay a 2.4 gigahertz antenna, and it was in fact 10 centimeters wide. I could get Wi-Fi like 3/4 of a mile from my house.
Holy crap.
Which was probably totally not legal at all. Because it was an omnidirectional antenna. It was probably just spewing out everybody's Wi-Fi. But it was very young, so not a lot of people had Wi-Fi then. But the antenna was literally, like, it had shielding around it, right? But it was like this big, around about that tall.
So like a Yagi?
Huh?
It was like a Yagi?
No, it was. It wasn't a Yagi antenna. I don't know what the actual shape of it was inside that thing, because it had this plastic protection around it. But I think it was just yeah, it was awesome. All right, the next question is LEO, MEO, and GEO satellites, right? And we find out quickly why none of us, if you live out in rural wherever, that GEO HughesNet is terrible, right? So it's really just a round trip time, right? Speed of light, how long does it take to get there and get back? So with low Earth orbit, I believe it was 5 milliseconds there and back. With the MEO satellites, it was 120 milliseconds, and then 238, I think, with GEO. Right, but it's the same formula all the way around. Just calculate the speed of light times twice the distance, right? So that's 1/4 of a second for GEO. It's a long time. All right, and then I believe the last one was hard. All sorts of wild answers here and there on this one. Oh no, we had a super easy question, which was how much bandwidth was to transmit your screen uncompressed across a 60 megahertz or with a 60 hertz refresh, right? So the screen was 25 by 60, or 2560 by 1600 with 32 bits per pixel, and then of course 60 hertz for the refresh. It turns out to be 7.9 gigahertz in order to do that uncompressed, which is why remote desktops are very compressed. All right. And then the last one. The last one was you need to send 6 gigabits per second of data over a channel that can only send 1 bit per second per hertz. It was there to make it easy. How many microns of wavelength is needed at 1.3 microns? So we can do it the same way we did this one. This time, we are looking for the delta of wavelength instead of frequency. So the delta frequency is equal to 6 gigabits per second. And we're going to start out with a wavelength of 1.3 microns. So what do we do? Well, we can find out the frequency of, we have this, so we can find out the frequency, right? So frequency, frequency is equal to 3 times 10 to the 8th over 1.3 microns, so times 10 to the negative 6. And so now we have frequency, right? So frequency prime, the delta is that number equals f plus 6 times 10 to the 9th. Well, if we have this number, then I chose 1.3. It was convenient out of the book, but it also makes a repeating number, which is very nice. Just can't remember what the repeating number is.
23076.
It's like 2037 something.
2307669, I believe.
230769.
I believe. Anybody else? I don't know.
So this number here, frequency, ends up being 230769.
Yeah.
230769230, I think. And then we had 6 times 10 to the 9th, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. The 6 goes there. So you end up with 230, 775, 230, 769, 230. So where do we go from here? We have 2 frequencies. Well, we can find out the wavelength of this frequency, right? The wavelength of this frequency is, so wavelength is equal to the speed of light over frequency, right? So that would be wavelength is equal to 3 times 10 to the 8th over that really large number. Even if you put it in microns and move the decimal point to there, it's still a big number. So then, right now you have 2 wavelengths, right? You have, so this first wavelength and then this wavelength prime, you just subtract the 2. And if you subtract the 2, you get 3.38 times 10 to the negative 5th microns. Or you didn't.
Yeah.
So you get 3.38 times 10 to the negative 5th microns, or 10 to the negative 11th meters. Really, really, really small number.
So that's I'm having difficulties analyzing the question.
Uh-huh.
And the reason why is because the wavelength is given in microns, but then you're also saying that the bandwidth is also giving in microns, like the spectrum space.
So this goes back to the question of, you go to the FCC and you license 1.3 microns to 1.4 microns, right? And your boss asks, your project consumes 6 gigabits per second, how much of my space are you using? Like, because if you license this, right, it would be divided up, you would divide it up into chunks.
Right. Well, you said makes
different-
more sense than what the question asked.
Okay.
That's what I'm getting at. So the difficult part of that question, and this is just general feedback, how many microns of wavelength is needed for this at 1.3 microns? So are we saying, so I didn't realize we were trying to figure out delta.
Yeah.
I thought delta was given as 1.3
Okay.
microns.
Yeah, I kind of
Okay.
I stopped 3/4 of the way through. I got to the big number, and then I multiplied it times 6 gigabits, thinking that was close.
That's fair enough. I can see that, so I'll give those points back.
Also on that problem, with the one before it, number 6, where you had the delta F equals
So,
times delta wavelength
yeah.
over.
There's an easier way to solve it.
I didn't know if you were gonna go over
If,
that.
yes. So this is the hard way, right? Which is probably the way you would actually use, because you would have a starting point and you can't really split the average, right? But if you could split the average, like on a graduate level computer science test, right, where we're just looking for ballpark numbers and not, you know, down to the 10 to the negative 15th microns, right? If you can't split the difference, right, then you can use the same thing that we did before. And we can derive a much easier formula. And this, if you split the difference, because of the way that quadratic will end up, you'll end up with your delta, is what you're looking for, is equal to the wavelength squared times the delta frequency over the speed of light.
This is the formula I'm familiar with.
Huh?
This is the formula I'm familiar with, since my background is physics.
Yes.
Use this formula to make it easy.
Yep. So again, this is that you have 1.3, right, and you're going to split both sides on both those. If you do that, then we can just plug in everything, right? So we'll have we'll have 1.3 times 10 to the negative 6 squared times 6 times 10 to the 9th, which is our gigabits per second. Over the speed of light, right? So that ends up being 1.3 squared is 1.69 times 10 to the negative 11th. Yeah, that's not the way to do
Negative 12.
it. Yeah. Just do 1.3 times 10 to the negative 12th times 6 times 10 to the 9th. Or, sorry, it's 1.69. So then 1.69 times 10 to the negative 3rd times 6 over 3 times 10 to the 8th. So then you're like 1.69 times 10 to the negative 11th Dude, get rid of 3, change that to 2. Which is 3.338 times 10 to the 11, negative 11. Which is 3.338 times 10 to the negative 5th microns. Much easier if you do it that way. But if that's only if you switch again. Either way, on any subsequent test or question or wherever, I will take the average. It's just way easier to calculate. And I'll try to word the questions better. Any other questions on physical? Everybody get the data link homework done. Because I will probably grade it tonight. All right. Cool. I don't have anything else. Can we get your homework in right now? Unfortunately, I printed them all out. Not all of them have names. So.
Test, if we have a question on the question, can we go to you and say, hey?
Sure. Well, you can, or you can,
Yeah.
whatever.
We're not gonna
So this might be a dumb question, but what's the easiest way to know if you want to use Shannon or Nyquist? Because I was looking at my answers, and every time I went to Shannon, I was using Nyquist. You know, multiply everything by 2 equals so.
Shannon has everything to do with signal noise ratio. Right? It's the maximum amount of data you could stuff in. And remember, that's a theoretical limit. So while there are some modern error correction and encoding schemes that get close to that theoretical limit, right, is really a theoretical limit. Right? Nyquist has everything to do with how much data you can send given your frequency. Right? So the really most easy way to determine is, was I given a signal to noise ratio? With the exception of that trick-ish question where it didn't give you it, it allowed you to make your own up, right? Any other questions?
Midterm will be over the physical and data link later.
Physical and data link only. So the data link is both the physical half of data link, right? Error correcting schemes, that sort of thing, and like media access control. So adding that third computer, contention, that sort of thing. And that's it. We won't do any network count.
The scores for the physical homework I'm inputting.
I got them right here. I just need to put them in.
Oh, yeah,
but
make sure.
I was just going to put them in, and then I realized that I printed them out, and not all of them have names on them. So I can put the ones that have names in it, and then you can say that one has a really good score, so that one's mine. All right, we'll do that. If you want to hang out, I'll give you your homework back. I just got to put it in the computer.